Add a tens to itself 10 times. You expect to land exactly on 1. But ask the computer whether the result equals 1, and it answers false. That single surprise opens a door into how computers actually store numbers and why a base 2 view of the world matters. Let's see why. Here's the code that started it. We set x to 0, then run a loop 10 times, each pass adding 1/10 to x. After the loop, we print whether x is equal to 1. The output is false, so we print the actual value of x, and instead of 1, we see 0.999999999999999, 16 nines, just short of 1. To Python, that value is not equal to 1, so the comparison returns false. This is the core problem. If we can't reliably compare floating point numbers, our programs can silently break. The fix starts with understanding how these numbers live inside the machine, and that means thinking in base 2. To understand storage, start with the easy case, whole numbers. Computers store everything in base 2 using only zeros and ones, so we need a way to turn a base 10 integer into its base 2 string. The algorithm builds that string one digit at a time. It starts empty, and on each step, it figures out the next binary digit and prepends it to the front of the string. A digit is either 0 or 1, decided by whether the current number is odd or even. Let's run it on a concrete number. Convert 19 to binary. The loop runs while num is greater than 0. Each pass does two things. Take num mod 2 to get the next digit. Then update num with num integer divide 2. Start with num equal to 19. 19 mod 2 is 1 because 19 is odd. Prepend that 1. Now update, 19 integer divide 2 is 9. We keep only the whole part and discard the 0.5. Is 9 greater than 0? Yes. 9 mod 2 is 1. Prepend it, so the string is now 1, 1. 9 integer divide 2 is 4. 4 mod 2 is 0 because 4 is even. Prepend the 0, giving 0, 1, 1. 4 integer divide 2 is 2. 2 mod 2 is 0. Prepend it, giving 0, 0, 1, 1. 2 integer divide 2 is 1. 1 mod 2 is 1. Prepend it, giving 1, 0, 0, 1, 1. 1 integer divide 2 is 0. Now num is 0, so the loop stops. The binary representation of 19 is 10011, kept as a string. Notice how the digits emerge from the bottom up. The first digit we computed, the remainder of the smallest number, became the leftmost digit because every new digit is pushed onto the front. Let's confirm that 10011 really is 19. In base 2, each position is a power of 2 and the powers ascend from right to left. The rightmost digit is 2 to the power 0, which is 1. The next is 2 to the power 1, which is 2. Then 2 to the power 2, which is 4. Then 2 to the power 3, which is 8. And the leftmost digit is 2 to the power 4, which is 16. Now add up only the positions holding a 1. The leftmost one contributes 16. The next two positions are zeros, so they contribute nothing. The next one contributes 2, and the rightmost one contributes 1. 16 plus 2 plus 1 is 19. The digits check out perfectly. That is exactly the value we started with. What about negative numbers? We barely need to change anything. At the very start, an if-else checks whether the number is less than 0. If it is, we set a negative flag to true, then convert the number to its absolute value. From there, the code proceeds exactly as if it had been handed a positive number. The conversion itself never tracks the sign because the digits come out identical either way. The only difference comes at the very end. If the negative flag is true, we prepend a minus sign to the finished string. So converting negative 19 reuses everything we just did. We flag the sign, take the absolute value to get 19, convert it to 10011 exactly as before, and then prepend the minus. The binary representation of negative 19 is simply minus 10011, the negative of the same result. Step back and see the shape of it. One short loop, repeated mod 2 and integer divide 2 turns any whole number into the zeros and ones a computer actually stores, and a single sign flag handles negatives for free. This is the clean, exact world of integers. The trouble we opened with comes from the other half of the number line, fractions. A value like 1/10 has no tidy, finite, base 2 form, so the machine can only approximate it. And those tiny approximations are what made our 10 additions miss one. Understanding how integers convert is the foundation. Fractions are where it gets interesting. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.